Good afternoon, calculus class today. So we would like to talk about the continuity. So this one, it's sections 2.5 from calculus, James Stewart. So definition of continuity. So a function is continuous at a number a. A is a constant. And we do have three different criteria. So we need to satisfy. So three conditions that we need to satisfy here. So the first one is that f of a is defined. And then the limit of f of x as x approaches a exists. And the last condition is showing limit of f of x as x approaches a is the same as f of a. So once we satisfy those three conditions, so that means the functions must be continuous at the value of x equals a. If one of those conditions fails, so that means the function is not considered continuous at that position, at the value of x equals a. So if the function is not considered continuous, then that would be considered discontinuous. So discontinuous, so we do have four different types of discontinuities. So the first one, so as you can see that there's a hole, and it's a straight line going through, but there's a hole in the middle of the line right here. So anytime that you see the hole like this, without any external point underneath or right above, so this one is called a non-removable discontinuity. So non-removable discontinuity. And then this one here, as you can see that there's a vertical asymptote here. So this one is called the infinite discontinuity. And then what about this one is quite similar to the first situation here. So there's a hole going through the line. The thing is that there's an other point and one of the external point outside the line here. And this one is lining up with the hole. So anytime that I see the point, like external solid point, either above or down below that open circle, so this one is called a removable discontinuity. Well, the reason why it's removable, so imagine that you just place the hole with the solid point. So that means the entire line will be considered continuous. Okay, so that's considered removable discontinuity. And now what about for the other situation here? If you see that the staircase function, so like an integer function, the one we talked about already, so it's like int of x. If you put it into the calculator, it's like an integer function or the staircase function. So this one is called a jump discontinuity. Okay? So we do have four different types of discontinuity. Non-removable, removable, infinite discontinuity with the vertical asymptote. And then the last one, the fourth type, it's called the jump discontinuity. Okay, so now let's move to the next page. So this one is nothing new, nothing special. So in order to have a function continuous, so the limit from both sides must be exactly the same. So the limit approaching from a from the left is going to be the same as the limit as x approaches a from the right. So therefore f of a is considered defined. So once you see the situation, so this one is just another definition of continuity. Okay, so once you verify that the limit approaching from the left-hand side is the same as the limit approaching from the right-hand side, and also is the exact same position as f of a, so that means the limit exists, and also the function is considered the same as the limit. So from the given graph here, state the interval on which f is continuous. So state the interval where f is continuous. So anytime that I read through the graph for the interval, it's all about the x value, so which means the x-axis. So reading from left to right, so as you can see that the function is continuous from negative infinity to negative 4. Well, because that at negative 4 the limit exists, but somehow this one is considered discontinuous. Well, because that is considered removable, non-removable discontinuity. at negative 4. So let's point out those positions where it's considered discontinuous. So at negative 4, and negative 2, and then at 2, and then at 4 right here, because it looks like this one is like a vertical asymptote. And then all the way, well, so for those positions, negative 4, negative 2, positive 2, and negative 4. So you find out those positions where the function is not continuous. And then the next interval, which is considered continuous, then that'll be from negative 4 to negative 2. Again, as you can see that the endpoint, while this one is closed circles, because that's coming from the left. So this one in negative 2 is closed bracket. It's a solid circle coming from the left. And then starting at negative 2 from the right, because this one is approaching from the right, so that one is not considered continuous. So at this position, so it's open circle, and it goes all the way to 2, all the way to 2. So again, this one is coming from the left-hand side, so at 2 here, it's open circle, open parentheses, excuse me. So that one is considered not part of the closed interval for the continuity. And then coming from the right-hand side here at 2, so that one is considered continuous because that's a solid circle. So that's why it's an open bracket at 2. And then it goes all the way to 4. Again, not included because that's a vertical tangent. And then the one coming from the right-hand side at 4 here, so that's considered open bracket. So 4 to all the way to infinity. So for those interval, you'll see that the function is considered continuous. And now for the next example, so you want to sketch the graph of a function has a jump discontinuity at 3 and a removable discontinuity at x equals 5, but it's continuous everywhere. Okay, so jump discontinuity at 3. So let's sketch that, the x-axis, the y-axis. So 1, 2, 3. So this one is saying that's a jump, so that means an open circle up here. Or we can say that this one is a closed circle as well. So the other part here, so that's continuous, so it could be any kind of random curve or like a straight line. And then what about f5? So that one is considered removable discontinuity. So f5, so 3, 4, 5. So somewhere over here, so it's connected. So this one is connected through. But don't forget, if that's removable, so that means there's like external point here, either right above or right down below that open circle. So here's a 3, here's a 5. Okay, so it could be any kind of random curve. But the thing is that everywhere it's continuous, so that means it's got to be connected from negative infinity to 3, and then 3 to 5, and then 5 to infinity. They're always considered continuous. So make sure that you need to set up the condition which is satisfying the given situation. So at 3, it's a jump discontinuity. At 5, it's a removable discontinuity. Okay, so now let's see what else that we have for the rest of this. So example 3, use the definition of continuity and the properties of limit to show that the function is continuous at the given number a. So again, so those 3 criteria. So the first one showing that, if we go back to the first slide, so f of a is defined. Okay, so that means the point, the y value, it's defined. It's not considered undefined. And the limit of f of x as x approaches a exists. And then the third condition is just the combination of the first and the second condition. So the limit of f of x as x approaches a, so that equals f of a. So now let's find out. So for f of negative 1, is that considered defined? There's no restricted value, so basically we can just plug in the number. So negative 1 plus 2 times negative 1, quantity to the power of 3, the little caret, that means the power sign. And then the whole quantity of this to the power of 4. So let's find out what that is. So negative 1 plus 2 times negative 1, so negative 2. And then the whole quantity of the sum to the power of 4. So that means negative 1 quantity to the power of 4. So that would be 1. So that means f of x is defined. And what about for the second conditions? Does the limit exist as x approaches a? So x goes to negative 1 of f of x. Does the limit exist? Well, it does, right? Because there's no any kind of restriction here. So basically this one, we can just plug in the number. So to find the limit, so we can define that by using f of negative 1. It's also what? 1. We just verified it. And then the third condition, we just compare that condition 1 and 2. They're exactly the same thing. So condition 1 is the same as condition 2. So therefore, while the limit not only exists, but also at that positions, the function is considered continuous. So therefore, f of x is continuous and x equals a, which is what? Negative 1. And now, what about for part B? So part B is showing that it's a rational function. Now this one is not giving you the exact point. This one is giving you the interval. So the way to verify it, this, we need to find out the domain first. The domain of g of x. Because that we need to verify the whole function with the interval. Not just at one point, okay? Unlike the first one, so the first one we just need to verify the continuity at one point. But this one we need to verify the entire interval. So one thing we need to find out is the domain. So one thing we do know that domain, the restricted value. So pretty much x can be any number except what? 2. So the way to state that the domain is from negative infinity to 2. And then union 2 to infinity. And one thing that we find out, the given interval with part of the domains, so basically they match. Since they match, so that means the interval right between 2 to infinity, it's also considered continuous. So that means for g of x, it's considered continuous on the open interval from 2 to infinity. Now, another thing that you need to verify here, it's about the one-sided limit. As you can see that this one is being bounded from 2 to infinity. It's right between 2 to infinity. So that means we need to take the limit as x goes to 2 coming from the right-hand side, from the positive. And then we need to verify that the limit as x approaches infinity. So we need to make sure that those limit exists at the end point. Okay? So the one-sided limit, so we got 2, 2 from the right-hand side, we can plug in what? 2 times 2.0001 plus 3. And then all over 2.0001 minus 2. So as you can see that this one is considered a constant. A constant divided by a very small negative decimals, negative 0.0001. So that means this one is considered negative infinity. So that means the graph goes all the way up to the bottom. Goes all the way down to the bottom, excuse me. So therefore, that's considered part of the reason why this interval is considered continuous. And the other thing is that the limit of f of x as x approaches infinity. So this one, we haven't gone over that yet. But the thing is that if you want to verify it, we can always take out the greatest common factor, top and the bottom. So for g of x, so we do have 2x plus 3 over x minus 2. So here we can just simply take out that 2. So we do have x plus 3 over x. 3 over 2. Okay, give me one sec here. So I'm just... Yeah, so that would be considered, well, we don't take out that 2. Instead of taking out 2, we take out the variable. Another way we can do that is by using the synthetic division. So once you divide it, you'll see that the x and the x will get canceled. But you don't want to use the synthetic division. You can always take out the common variable, x. So we do have 2 plus 3 over x remain, because we took out x on the top. And then the denominator, also we took out x. So we do have 1 minus 2 over x. As you can see that x goes to infinity, so 3 over infinity, that would be a very small number, so this one basically got cancelled. This one too, so 2 over infinity, it's a very small number. It's almost getting close to 0. So what's left here, x and x got cancelled or reduced. So we do have 2. As you can see that the limit exists for both of them. So the limit as x approaches 2 from the right, and the limit as x goes to infinity. So since both those limit exist, so that means for that interval, the domain of the functions, so guarantee that g of x is continuous on the same domain. So anytime that you need to verify the continuity with the interval, so not only you want to show the domain, but also you need to show the limit as x goes to the left bound, and the limit as x goes to the right bound. If both those limit exist from those two bounds, so that means the function is continuous with the exact same given domain. Okay, so now let's see what else that we have for the next one. So sketch the graph of function and explain why the function is discontinuous at a given number a. So we do know that cosine of x is it's an upside down bell curve. But this one, there's a restriction. It's a piecewise function, so this one is only for anything that x is less than 0. So for the normal bell curve, we started right here. So let's say that you want to continue with the rest of this. So for the rest of the cosine curve. Okay, like that. And then the amplitude is always from -1 to 1. So again, at 0 is not included, so that means at 0 here, that's an open circle. And then for f of x equals 0, so f of x equals 0, so that means here, so that's a solid point at the origin, so that's 0, 0. And then the rest of this, for x is greater than 0, so it's 1 minus x squared. 1 minus x squared, so that means it's considered a upside down parabola. But it thinks that for the restricted value, so that means only like a half parabola here. So it goes down all the way like this. So now, you want to explain the reason why the function is discontinuous at the given number a. So the way to define it, so after we sketch the graph, we just need to find out the limit, the one-sided limit. So we just need to verify the one-sided limit are not consistent. And then we can show that the function is discontinuous. Because that, going back to what we have right here. So the limit, in order to have a function being continuous at that position, so the limit from the left at a is the same as the limit as x approaches a from the right. If both limits are not the same, so that means the function is not considered continuous. Okay, so now let's do that one. So we do have, let me just erase this one a little bit. So let's just verify the limit without using the graph. Well, certainly can look at the graph again. So limit x goes to 0 from the left. So that means we're using the first piecewise function. So plug in 0, so we do have cosine of 0, then that would be considered 1. Okay. And now what about the limit as x approaches 0 from the right? Well, the limit as x approaches 0 from the right, so this one is considered 1 again, because that 1 minus x squared, so that's the one we're using, approaching from the right. So that one is considered 1 minus 1 squared. We're not using cosine anymore. It's 1 minus x squared, the quadratic. So a lot of people might be wondering, wait a minute, the limit from both sides, they're actually the same. But don't forget, what about the point defined at a? What's f of 0 here? That's considered 0. So therefore, the limit, while the limit exists, but somehow this one, condition 3, it fails. So in order to have a limit exist, and also the point is defined, but also don't forget about the third condition. The third condition showing that the limit, the value of the limit, is the same as the value of y, of f of a. As you can see that right here. If this one is not the case, so therefore the function is not considered continuous. So that would be discontinuous. Again, the limit from both sides, they're exactly the same. But somehow, at this position here, it's not the same as those two limits. So therefore, it's discontinuous. Excuse me. Okay, so limit as x approaches 0 from the left, it's not the same as f of a. And this one is not the same as the limit approaching from the right. So therefore, the function is discontinuous at x equals 0. So the value of a is a equals 0. Alright, so now let's see what else that we have for this. So the following types of functions are continuous at every number in the domain. So basically, anytime that you see this type of functions, you'll see that, well, the graph is always continuous from negative infinity to infinity. Also showing that the domain is negative infinity to infinity. So things that we have, such as what? Polynomial, like a random curve, goes all the way from negative infinity to infinity. Root functions, such as what? Cube root, fifth root, seventh root, it's always continuous. So we're talking about the odd root, okay? So let's just specify it. If that's an even root, there's like a restriction. So the even root, the restriction would be consider x is greater than 0 or equals 0. Trigonometric functions, so that's the one we're talking about, such as what? Cosine and sine. If that's tangent, cotangent, secant, and cosecant, that would be exception. So cosine and sine is always considered continuous. Sine curve is always what? Roller coaster. And then cosine curve, it's a bell curve, the one that we did before. So gotta be careful with the name. So any kind of polynomial function, odd root function, trigonometric functions such as cosine and sine, inverse trigonometric function. So inverse trigonometric functions, so things that we have like inverse of tangent. So that one is like this. Kind of like a cube root function, but it's being bounded with the asymptote of the range, the horizontal asymptote. Exponential functions, so exponential function is like exponential growth or exponential decay. Exponential growth or exponential decay, so things like that. So they always consider continuous function from negative infinity to infinity. And then for example 5, explain why the following function, misspelled it right here. So the following function is continuous at every number in its domain. State the domain. So as you can see that this one, well, this one's a combination, it's a product of what? Exponential function and the cosine trigonometric function. Well, basically this one just guaranteed that the product of the function, the product of those two functions must be continuous. Because one is what? Exponential, the other one is cosine of trig function. So basically this one is satisfied the condition we have. So once we find out any type of those functions considered exponential or trig, so that means the product, because once you multiply them, it's called a product of an exponential function and a cosine trigonometric function it's also continuous. And also, what about the composition? Compositions, same thing. So this one here, so square root, but the things that e to the power of square root of x. So that means it takes care of the everything here for the domain. Okay? So this one, exponential function, sine curve. Yeah, this one is supposed to put in cube root, not square root. So the first inner function is called the odd root. And then exponential function. And then the sine functions. So the composition of root exponential function and sine trig function. Okay, I'll just put it right here. And sine trig function. So therefore, the function is considered continuous from negative infinity to infinity. So basically just describe what's happening here. Again, this one's supposed to be cube root, not square root. If that's a square root, there's a restriction. Okay, so now let's see what else that we have for the rest of this. So you want to prove that f is continuous from negative infinity to infinity. So basically, again, if that you need to verify it's continuous, we need to show the domain. So for the first piecewise functions, so the domain for this one, x squared, well, basically x squared without the restriction is always from negative infinity to infinity. So with the restrictions, so the first domain, so this one is considered negative infinity to 1. And then what about for the radical functions? So normally without the restrictions, so the domain for this one is from 0 to infinity. Well, because that square root of x is like this. But with the restrictions, so this one started at 1, and it goes all the way to infinity. As you can see that basically this one, it matches with the domain. But one of the critical position here we need to verify, it's the limit at 1. So we need to show the limit as x goes to 1 from the left. And once we're being able to prove that the limit from the left is the same as the limit from the right, and that's the exact same position at 1 for f of 1. So that means, the function is continuous at that position. So the limit approaching, the limit as x approaches 1 from left, so we're using the first one, so it's 1 squared. And the limit as x approaches 1 from the right, so square root of 1. And then what about that f of 1? F of 1 is defined. It's actually what? 1. If you just plug in the number back here. So 1. So square root of 1. And try to verify that it's all the same. So 1 equals 1 equals 1. So therefore the limit exists at 1. And therefore the function is considered continuous from negative infinity to infinity. So again, so first thing that you want to show, the domain. And then the second thing that you want to prove, the critical value, the positions that where you see that close parentheses 1, open bracket 1. So just find the limit. One, it's approaching from the left, the other one is approaching from the right. And once you're being able to show that, it's the same as f of 1. So therefore, the function is continuous from negative infinity to infinity. Okay, so now what about for the next one? So for what values of a constant c is the functions continuous on negative infinity to infinity? So again, this one shows that limit from the left at 2 must be the same as the limit as x goes to 2 from the right. So in order to show that, so we just want to set this to piecewise functions equal to each other. And one thing for sure that they share in common is the value of x. So they're both 2. So we plug in x equals 2 for both of them. So we do have c times 2 squared plus 2 times 2. So that equals 2 cubed minus c times 2, or 2c. So we do have 4c plus 4. So that equals 8 minus 2c. And then the rest of this, we're just solving the linear equation. So 4c plus 2c, then that'll be 6c. And then a minus 4, then that'll be 4. And then solve for c. So divided by 6 both sides. So we do have c equals 4 over 6. Which is what? 2/3. So in order to have a function continuous from negative infinity to infinity, so the limit at those critical positions must be exactly the same. So the way to find it, so we set them equal to each other, and then we solve for c. Again, x, that would be the critical value, which is 2. Okay, so now let's see what else. And the last page here is the intermediate value theorem. So what that means, well, we actually talk about this a little bit in pre-cal. So if f is continuous on the closed interval from a to b. So here's the closed interval from a to b. It's all about the part of the interval on the domain. Okay, from a to b. And one thing for sure that let n be any number between f of a and f of b. So f of a here, let me see. So this position is what? A comma f of a, just like the xy values. And then up here, so that would be considered b comma f of b. So there's a value n somewhere right here. Okay, n. Any number right between f of a and f of b. That's what we have, right between the range. So where f of a, it's not the same as f of b. So here's one of the criteria we need to satisfy. F of a does not equals f of b. Okay, let me just annotate it. Oh, shoot. Let's just retry, redo, undo. Undo. Okay, let me just erase that. It happens all the time like this. Okay, so once again, the condition we need to satisfy, so this one, so the function is continuous on AB, so that's the first conditions. And the second condition is that f of A is not the same as f of B. Okay, so f of x is continuous on that interval. And then f of A is not the same as f of B. Well, what happens if this one, they're all true, if they're all satisfying? So that means there exists a number c in between a and b. So c is right between a and b here. So such that f of c equals n. So f of c here, so that equals n. Well, sometimes more than one solution, it's not just one. There's so many n right here. You can say that, well, because it doesn't matter whether that's a midpoint or not. It can be any number right in between that f of a and f of b for the value of n. It can be here, it can be over here, it can be up here, it doesn't matter. It can be lower, it can be higher. Okay, so the way to find that out, so we need to satisfy these two conditions. So f of x is continuous on that closed interval right between a and b. And then f of a does not equals f of b. If that's the case, so that means there exists a number c such that f of c equals n. Another way you can put it, so you can put it like a conditional statement. If this one is true, then f of c equals n. And where c is right in between a and b. Okay, so use the intermediate value theorem to show that there's a root. I actually duplicate that a of the given equation in the specific interval. So as you can see that this one is considered a quartic trinomial to the 4th degree quartic, or to the 4th degree trinomial, 3 terms. So one thing that we need to verify, so let's say this one is the function, so f of x. So we do know that if that's a polynomial, so that means the functions, the first condition is already satisfied. It is continuous. Well, it's not just continuous from 1 to 2, but it's continuous from negative infinity to infinity. So on the interval from negative infinity to infinity. And now the things that we need to show is that the closed interval, a and b. So we want to show that f of a is not the same as f of b. Then we can find the value of c there. So the way to do it, so you want to prove that f of a, so f of 1, so that's 1 to the 4th power plus 1 minus 3, so that would be what? 2 minus 3, negative 1. And then f of b, so f of 2, so plug in 2 for x, so we do have 2 to the power 4 plus 2 minus 3, which is what? 16 plus 2, 18 minus 3, so then that would be 15. So obviously negative 1 is not the same as 15. And then we also satisfy the second conditions. So f of a does not equals f of b. And now we can just solve for zeros. The way to solve for 0 here, so you probably have to use a calculator for this. Because once you find out the solution is not going to be considered rational, it's going to be considered irrational. And that 0 is going to be right between 1 and 2. So once we prove that the conditions we satisfy, we can find a 0 here. So that means we're going back to Algebra 2 or pre-cal. And a lot of people might be thinking about using the rational 0 theorem for P over Q, but somehow this one, none of the rational 0 would work. Okay, let's try to use the rational 0 theorem so we can show the synthetic division. But the thing is that it's not going to work for this type of problem. Because all the 0, either they might be considered imaginary or they might be considered irrational. So the way to deal with this, we want to put it into decimal. So x to the power 4 plus x minus 3. Okay, let's use decimal. So we do have y equals x to the power 4, caret 4. Bring down the cursor. Let's see, minus plus x minus 3 plus x minus 3. And as you can see that we do have two zeros. One is in the negative region, the other one is in the positive. Again, make sure that the position that we find out, it's right in between the value of a and b. So the value of c here, so 1.164, it's right in between that the boundary, 1 and 2. So the value of c, the one that we found out, it's about 1.164. And then you want to verify what that is. So find out what f of c is. So f of 1.164, because that would be the value of n. So looking at the graph, and that's just what, 0. So the value for y, so then that would be 0. Because we're looking for the x-intercept. Okay, so that's 0. So basically just find the value of c. So find the value of the root. And that's exactly what we're doing. And then the other one is quite similar. But the thing is that before you do it, you want to bring everything together to one side. So cosine of x minus x. And that would be considered f of x. Again, we need to satisfy the condition of the intermediate value theorem. So plug in that a and b. So f of 0. So we do have cosine of 0 minus 0. Then that would be 1 minus 0, which is 1. And then cosine of 1, so we do have cosine of 1 radian. We don't know what that is. And then minus 1. Well, obviously this one, they're not exactly the same because this one's going to be a small negative number. So therefore, we satisfy the condition. Again, the other part is that the function is continuous always from negative infinity to infinity. Because this one's a trig function, the other one's linear. So the function is continuous. And f of a, it's not the same as f of b. So again, put in the functions. So enter the function into the calculator and find out the x-intercept. Cosine of x minus x. Okay, so y equals cosine of x minus x. As you can see that the function is continuous. And for the point here, the x-intercept, it's about 0.739. See that? It's irrational. So for the value of c, for this one here, 0.739. And what about that f of c is always 0 here because that we're looking for the x-intercept. Okay, so again, any questions, any concern that you have, or things that you still kind of confused or a little bit struggle, so make sure that you need to come by for the office hour or the after school tutoring, and you're more than welcome to watch the video as many times as you want. Okay, so try to use those key features: pause, rewind, fast forward, and also put in comments. If I see any question that you have the comment bar, I try to answer those questions as soon as possible. But make sure that you need to come by for the tutoring time and also the after the office hour. Okay, so those are the time I should be available. Okay, so thank you for watching the video today. So I'll see you guys next time. And you guys take care.